So, for the ones who don't speak whatever I tried, do the talk in English. So we talk about knowing your data. And let's see. So, question, when you write programs that process data, I mean not trivial, but really big amounts of data, do you worry about what your data looks like, or do you just use the default mechanisms to work with it? Anybody who looks further into it? Good. So, the thing is why we should make use of it, or could we make use of it? And so we usually don't have to bother because we have actually very good algorithms, and they kind of have this one size fits all, and they work well, and it's okay. But sometimes we have very big data, and we want to look further into it. So one example is when you write hash codes. Who just gets his IDE to makes his IDE create the hash code, and who writes the hash code himself and thinks about it, what to put in and how to put it in. So the point is, you have like this object, and this object has like a couple of attributes, and you kind of get these kind of objects, different ones, and then you could look which of the attributes gives the highest amount of surprise. So if you have, for example, a person, yeah, and then you have the birth date. So there's only 365 birth dates, so the amount of surprise from the birth date is not so much, because there's only this 366 choices. But if you take the name, usually, especially last name, gives a lot of surprise. Unless you're in a country where everybody is named Kim and Park, then you have to look into other attributes. So it's interesting to know where you get the highest amount of surprise, and that's usually the stuff that you should put into the hash code. So that's something like this. And so the auto-generated is often okay, but not if we really want to push it. So what we want to expect, the first thing is we need to fulfill this contract that it's compatible with equals. So if you break that, then your whole program is just kashmar, okay? And the next thing is you want a low collision rate. So you want the hash codes to be different. So you need something that gives you a big surprise, because that gives you different values. And then the next thing is you want it to be easy to calculate. So you can put all the attributes that you compare and equals in, and then it's the best low collision rate, but you waste a lot of time calculating something with the gender and the birth date, which doesn't give you a lot of additional information. So restrict it to wherever you get already enough difference. So that's this. And there is another issue, that is sorting. So when we sort, that is language dependent. So you have these issues that you have like German letters, and then there is Cyrillic letters and whatever, and you have different rules for each language how to sort that. But that's kind of an issue which you already deal with when you use the right libraries. It's not what interests us today. Today we look at performance. So we can use these library functions to sort, and they do a good job. And we learn that the best possible way is log O big N log N. Yeah, we proved it in some of us at least. And we learned that you don't care, actually use quicksort, and that normally is good enough. But let's see. That's kind of okay for small data, yeah? But let's see if we can do better than this. So we have these usual guys, quicksort, merge sort, heap sort, basically some tweaked versions of it or some combinations, and they are quite good. But we want to be better. So there is this algorithm flash sort, and it sorts in O of O big N, which is impossible, as we have proved in university. But it does sometimes. So we had it's at least in my tests, I ran some tests on it, it was faster than the other guys, yeah. Unfortunately, quicksort won always against the other two, but you can tweak them, but flash sort beats them if the data set is big enough. So let's have a look. It's basically the idea of quicksort. being pushed one level higher. And we'll see why we can beat this barrier. So in Quicksort, we split our data into two boxes. We take an arbitrary element, which we hope is the median, and then we split it into two equal parts. If it's the lowest one, we just have one part, and then we have O n squared if we repeatedly get it like that. But if we have a good data set, usually we get somewhere near n log n because it splits pretty much in equal parts. But in flash sort, we immediately split in, if we have n objects to sort, we split in n half number of boxes immediately. So we run through in one step and see how big these boxes are. And then we put the data immediately in these boxes. And then we just have to sort the small boxes, which is nothing. They even recommend to use the insert sort or bubble sort for that, but you don't have to worry about it. But this thing works very well. But the problem is we need a metric. So we need kind of an estimation of the position. And that's the cheating of it. Because if this metric is very well and very evenly distributed, then we know much, much more about the data than we usually do. And we don't have this thing in our classes. So we have to care about it. And so that's the reason why we need to worry about using quicksort and these things, because normally they are like running out of the box. And if we want to do this really fast thing, we really need to know our data and need to find a metric that is really evenly distributing the data. So it is kind of a hash code, but it has the additional rule that it's compatible to the comparison function. Yeah, so it's a monotonous hash code. And that needs to be tuned like a hash code, so you want to have a big difference and you want it evenly distributed. So to do that, you need to know a lot more about your data, right? So the next thing that we can think about is the issue of compression. And we have these things like gzip and some other things that are very well at compressing big files. But sometimes we have like smaller pieces of data. Just think about it when we have strings. Our strings are usually encoded UTF-8 or UTF-16. And like say for East Asian language, UTF-16 is very good because one character or one code point is occupying 2 bytes, but it's kind of almost a whole word. And if we have like Western European languages, then usually most letters go in 1 byte, so that's also kind of okay. But here in Ukraine, where the Cyrillic alphabet is used, you have to use 2 bytes with either of these 2 common encodings, and you get only 1 letter out of it. So the whole thing gets very long, which normally doesn't matter because we have a lot of memory, a lot of power. But when you store a lot of these data, you can't run gzip on all the strings, because then gzip has a lot of overhead to run. But you can think about it that you have specific compression for small pieces of data when you put in the fact that you know what language it is. So a language can also not only be Ukrainian, it can be like something like names of Ukrainian cities, or it can be temperatures, or it can be something, whatever. And then you know certain things occur more often, and the things that occur more often you make shorter. That's the idea. So, yeah. And if you have like one compression function that is specific for certain language, you can apply it even to shorter strings. And this overhead that you have in the header of the gzip file, you store only once in your function. It's kind of hard-coded. And for long files, of course, it doesn't make any difference because the overhead is neglectable. and something to think about in terms of this compression when you do encryption. It's also like this, that we have very good things for encryption now, and we transmit data and store data, and it works very well that our neighbor can't read it. But we have to think there's countries that have big organizations, and they don't tell what they know. And we don't know what they can do in today. We don't know what they can do in 20 years when they have quantum computers and they have stored all our traffic somewhere, and then they go back and see what we did 20 years ago, analyze that. So the general rule that is always true when you encrypt something and there is little information redundancy in what you transmit, then it's always like that it's very hard to crack it. You need to guess the key, and usually you have redundancy on the input, and then it's enciphered, and then you get some output, and because of the redundancy you might guess the key, and then you can read everything. But if there's less redundancy, then it's harder, even with quantum computers in 20 years. So that's very basic ideas. The problem is it's kind of not something that we all do, so it's more like ideas where we should go when we process bigger data, and we have to work on it because it's not what we get out of the libraries, out of the frameworks that we are using. But I found these things personally useful in projects that I did in the past. So I think it's a good idea for big data. Thank you. So you might have questions. We have time for questions. So please.
Have you already applied this approach to live projects?
Yes. So I had once a project where we actually processed very big data. I can tell you what it was. So for the bank, they printed certain bank papers, yeah, and then they had to be organized, that you print as little as necessary and organize it well. And the data arrived at certain time, and then it was printed, and then the post took the container at a certain. So you had a certain amount of time, you needed this much for printing, and had only like 2 hours left for processing. And this thing simply ran out of memory and crashed before the 2 hours were over and didn't give the results. And so we replaced the string class by something that we had written ourselves that used only, let's say, less memory. And then this thing survived its task. Well, it was like millions of, let's say 1 million, no, 1 million letters had to be processed, yeah? Not every day, but on some days. And they had to be processed in a certain limit of time. And each letter contained address and some metadata and whatever. And we had it was done in a time when we still had 32-bit constraints. So this thing simply crashed. And yeah, just like that. Yeah. Any more questions? Okay. Thank you.